we had talked about what had we talked about? Yeah, yesterday we had talked about this figure of merit and figure of noise of amplifiers and how does noise affect us. Today we will talk about and also yeah, we talked about figure of noise and we had introduced the notion of the figure of merit. Today I also talked about the uh, propagation losses briefly, but earlier I had thought that we would skip the propagation losses altogether, but it seems that the story doesn't complete without them. So I'll just give you a formula without a derivation because this requires a lot of electromagnetics, and since you haven't covered that as of now, let's simply state the formula. When you complete the course on electromagnetics and maybe then you can derive it yourself. But for now, just so the propagation loss. So if we transmit power PT, then the received power PR is given as PR equals LPT, where L is the loss and is this is the simplest possible propagation loss. There are other forms as well, with lambda being the wavelength being used for transmission and T being the distance between yeah. So Bhavnik, the problem is I'll be blunt, the TAs should be competent enough, or I should be able to trust the TAs that they will get the answers right. Something I don't have this year. In a 101 like course where you have everything, personally I do not like the 101 way of checking papers, and that too is done when you have a closed set of TAs who are packed in a room and made to do slave labor. This semester we do not have that luxury, and the kind of questions that are for this kind of a course, you cannot rely on that kind of marking. Everyone would be hit hard. Yeah, it will be. I don't know whether it will be worse than these on multiple choice questions, but it won't be anything good. That I'm sure. Yeah, d being the distance between the transmitter and the receiver. So L in decibels can be written as 10 log 10. Sorry. Four pi by lambda square minus, plus 20 log 10. Fine. Where lambda and t should have the same units. Fine.
Yes, sir.
Okay, great. Also, due to the also it is conventional to measure.
Sir, shouldn't there be a square on 4 pi as well?
Oh yeah, so rather I would write this. Fine.
Yes, yes, sir.
Yeah. Transmission line losses in terms of decibels per kilometer. You can also approximate it like that. Now, the last topic of analog communication. Repeaters. So you say that at the receiver end, you know that you want a certain SNR. So a certain target SNR, and we know the noise power. So noise, we reduce it to basically thermal noise, and because of that, we don't know the noise power at the receiver. Fine. This is okay.
Yes, sir.
So, yes, sir. So based on this and the knowledge of the propagation losses, we can decide on transmit power, right? If we know the propagation losses and if we know the transmit power, if we know the noise power at the receiver and we know that we want this much SNR at the receiver, then we can decide the transmit power. Not a big deal.
Yes, sir.
But we have to work with Yeah. So that, yeah, people are messaging on the group. Anyway, but we have to work with practical power. So have you come across this term, power amplifier?
Yes, sir.
Good. How?
Power, is it same as normal amplifier or is it different?
No, power amplifiers are a totally different beast.
No, sir, not
You,
yet.
oh, not yet, then you possibly won't come across this thing. So power amplifier, if I talk about a regular amplifier, say you have the voltage divider bias is the most stable one, right?
Yes, sir.
Yeah. So if I talk about a normal amplifier, these are the no, common emitter configuration. These are the characteristics, right? These are the characteristics of a output characteristics of a
Yes, sir.
transistor amplifier, and these are the different values of IB. So this is these are so now what in case of a communication signal, what I would want is that what we have stressed upon multiple times is that we want the signal intact, right?
Yes, sir.
If we want the signal intact, it means that we should be operating in this small linear region, because
Yes, sir.
if we want the signal intact, then the amplifiers that we work with should all be operating in the linear region, that is for the same input, or the input and the output is the a linear function of the input. That's what we want.
Yes, sir.
So we operate in this small region. We limit the voltage and the base current to this, and that's how we choose the operating point, right? You have chosen, you have
Yes,
you
sir.
have seen how do you choose the operating point of a transistor amplifier, that you would have
Yes.
done in detail. That's a part
Yeah.
of biasing, I believe. Yes,
Yes.
that's a part of biasing. So that you would have covered in 101. Yes, just a second.
Yes, sir. We covered it in our last course
Last
to
line.
analog circuits.
Sorry, you have covered this, right? So the thing is that in the linear region, the transistor amplifier is it reproduces the input exactly, but at the same time it is highly wasteful on power, or it's the power efficiency is quite low. To get the maximum power out of a transistor amplifier, you have to drive it in a nonlinear region. Agreed?
Yes, sir.
Yeah. So the choice is between between linearity and power efficiency. So you want high power, an amplifier that is power efficient as well as linear. You cannot get both. So what you do, and in order to transmit at a high power, you would be wasting that much power if you try to transmit at a high power, right?
Yes, sir.
So what we generally do is that, and obviously it's hard to design amplifiers that can transmit at a high power and stay linear because they'll heat up. So you'll not only be wasting power, as you operate to move towards higher and higher powers, the amplifiers will themselves become unstable. So high power linear amplifiers are a distant dream. What we have instead are low power linear amplifiers. And what we do is that transmit at some power, and this is the receiver. But we cannot, with this power, we cannot cover all this distance at the desired SNR. So what we do is we place a repeater here. So a repeater is basically a receiver and a transmitter. It receives, amplifies, and forwards. Receives, amplifies, and forwards. So we can put multiple such receivers here, and we'll therefore get, yes. So basically, we are that's what we are doing. We are stacking multiple low power amplifiers at a distance. But so the amplifier gain is not a problem. The problem is the power that an amplifier can handle. So we transmit, we let the power drop down slightly, amplify it again, transmit, let it drop down slightly, and so on. So in an ideal world, this would have been good. But the problem is that, as we have discussed earlier, each amplifier adds its own noise. So if the noise power here, so if the noise power is and not B of, if the ambient, then Pn1 or Pn0 is and not B. Pn1 is times F1. Fine. F1 is the, yeah, F1 is the noise figure. And so on. Fine. This is okay. So if we transmit PT sent, then so consider a simple system. This would help you. So the noise power is the ambient. Fine. So then you transmit PT, receive LPT. You receive LPT here. So the input SNR to repeater is LPT by fine. The output SNR L by F PT by fine. This is okay.
Yes, sir.
Yeah. Good. So now treat gain L and we can look at channel and the amplifier as the cascade of two amplifiers. Fine. This is okay.
Yes, sir.
Excellent. So from what we had yesterday, the overall noise figure of this channel amplifier cascade is F equals, or rather F, let me call it F prime equals this. And you can actually extend this by using the same logic. Same logic. You can generalize this for k repeaters with f equals L1 FA1 plus L2 A2 minus 1 divided by L1 by GA1 plus and so on. Okay, so you can, so these are just formulas, you can look these up, and these are not hard to derive as well. So based on this, you can calculate the transmit power, the received power, etc. So based on this, you can say that, okay, I have, this is my transmit power. These are the repeaters. These are their respective noise figures. This will be the overall noise figure of the network, and this is the received power, and this is what I want at the receiver. So that way you can calculate the received power, or the power that you require to transmit to get a particular received SNR. Fine. Any problems with this?
No problems.
Okay, great. So this finishes the analog communications part. So this finishes the analog communications part of your course. And now we have to start the digital communications part. So I'll be back in a minute. Yes. So this completes the analog communication part, and we want to start digital communications, and I've kept the pen somewhere. So yeah, this is embarrassing. Yeah, I found it. Yes. So yes, let us start digital communication. So I'll move to the presentation mode again. I'll repeat this presentation for your digital communications course, but Yeah. So I'll be repeating this presentation for the digital communications course, but anyway, let's courses. Yeah. So you have seen the so you have seen the basic block diagram of a communication system. Now I'm showing you the basic block diagram of a digital communication system. Can you guys point out the differences? Or actually rather what I'll do is I'll copy and paste this into I'll copy and paste these into OneNote. This and yeah, so I'll come to that analog to digital conversion and I'll paste the second slide here. So,
So we can only see the PPT.
yes, I know that. I'm yeah, so I'll just I'm moving back to OneNote. Now can you see it? No,
Yes,
you
sir.
yeah, you
Ah,
see the Teams window.
yes, sir.
Now you can see OneNote. So I'll use red. So use a thicker red. So not this thick. System. This is a general communication system. And this is a so this we have covered. We have talked about sources. We have talked about how to put the information from the source to the channel modulation. We have considered the errors produced by the channel noise. And we have talked about how to get the information back from a noisy modulated signal. Right. This is all. This is what we have covered. So the question is that why? So one thing we know that all practical sources of information are analog. All practical sources of information are analog. Speech, pictures, video. These are our observations from the sky. If you talk about scientific discoveries, then observations from the cosmos, the telescope, telescope images, everything. So basically for us, signals are anything that we can perceive as humans. So or for us only those signals matter that we can perceive, and our perception is limited to sight, sound, smell, to some extent touch, and the taste. Yes. So but if you think about it, sight is an analog receiver, sound is an analog receiver, smell, we have smell, touch and taste we haven't used for long distance communication till now. We have only used sight and sound. Smell is used for medium distance communication, but not for long distance. Yeah. So yeah, ants use smell for, but we are not designing communication systems for ants. So for as humans, we all the sources, and even smell is I don't know, but smells would be analog signals if we think about it. So all practical sources of information are analog. Then the question is, why digital? Why digital? Guesses?
Because it is easier to separate noise from the digital signals. Like,
Uh, Kind of, yes. So digital signals, you have the luxury. So we'll talk about the noise, the effects of noise in digital signals, but
So
easier
it is easier to
storage,
send.
easier storage. The biggest convenience in digital systems is the development of digital VLSI logic, or digital VLSI circuits. Analog VLSI circuits are ridiculously hard to design and involve big money. So analog VLSI designers get paid a lot, and you all of you have done that instrumentation lab, and you have done that digital lab, right? So
Mm,
instrumentation lab was actually, most of the instrumentation lab was actually analog circuit design. Would you agree with me?
yes, sir.
And most of the digital circuits lab was obviously digital circuit design and coding.
Yes, sir.
So which one gave you nightmares?
Kind of both, but
Digital lab gave nightmares. Why?
Analog.
Yeah.
analog.
Analog gave nightmares.
Yeah, analog gave nightmares. The digital lab is so digital lab in from where I have learned digital lab, the experiments are digital. Mostly they work, and mostly you can code stuff. So digital lab,
the nightmares were not the logic, it was the hardware implementation, the wires and stuff.
wires and stuff. Okay, but the design isn't hard in digital lab, but yeah, wires and stuff with the what do you call it? The kind of ICs that we have, we would still be
Yes,
using
sir.
those 74 series. 7474 is 7400 is the NAND gate, and you are expected to do everything using that, right?
Yes, sir.
Yeah. So that's a separate problem, but there you can, it's easier to debug, it's easier to pinpoint. Analog circuits, you are stuck and you are stuck.
Yes, sir.
It works for the same circuit works for 1 milliampere. You go to 5 milliamperes, the resistor sizzles and burns. Happened to anyone?
Yes, sir.
Yeah. So there's, you apply slightly larger current, you change some parameter, and there's a sizzling sound, and something will burn. That doesn't happen in the digital lab. So digital VLSI or digital circuits are easier to design and manipulate, and digital VLSI led to easier implementation. So
They are
the,
also cheaper, right?
yeah,
Than that.
because of the scale, they are cheaper. Because they can be produced in mass scale, and they are easier to use, they are cheaper. And there's one outstanding achievement that was made possible. So this made the made an easy, or this made possible an easy implementation of FFT. So FFT is a good example of the no free lunch theory. What you have is that you have a computational complexity. So we know that DFT is required for processing discrete time signals and has a computational complexity of order of n square. This you would have covered in your DSP course, right? Right?
Yes, sir. O of n square.
And but in 1960, Toki and another, let me, since I have the luxury of internet, let me use Wikipedia and yeah. So in 1965, Cooley and Tukey, this was actually discovered by Gauss, the same Gauss of the Gaussian distribution. But in 1965, Cooley and Tukey made this popular by showing an efficient hardware implementation using, so in FFT, in DFT you need a single adder and a single multiplier to calculate the DF to a classical DFT or the Godzel algorithm. You require a single DFT, a single multiplier and a single summer, but for FFT you actually trade off the computational complexity for the hardware complexity, and Cohen and Tukey showed that showing an efficient using VLSI architectures. What this enabled was now FF digital circuits and these circuits are so you want to suppress certain frequency bands. You need to derive a band pass filter. Complicated process. You have to have the exact inductances and the exact resistors, right?
Yes.
If you
Yes.
use this, but instead, if you decide to process the same signal digitally, you can convert it from analog to digital, take the FFT, use a simple numerical filter and get anything you want. That's the beauty of digital signal processing. You can reduce any analog signal operation to a code. You can reduce anything that can be done by a bank of resistors, capacitors, inductors, amplifiers, and whatnot to a programmable code. That's why digital signal processing is so important. You tell me that, okay, I want a diode detector, or a diode detector involves a rectifier followed by a low pass filter. I say, okay, give me the samples of the analog signal. I take digitized version of that analog signal, chop off all the negative parts, that gives me the rectifier, and then simply low pass filter it. And low pass filtering simply means I take the FFT, chop off the higher frequencies, and allow the lower frequencies. The diode detector is reduced to simply this thing. I can create a phase lock loop. I can create any analog circuit. I can create a digital equivalent of any analog circuit that you can imagine, and still save money. That's why digital signal processing is such an important, or possibly one of the greatest inventions of the 20th century. And obviously, in the digital case, there are something called error correcting codes that allow us practically, or that theoretically allow us noiseless transmission. So that's why we are so obsessed with digital communication, and all the modern communication systems, including your phones, televisions, the internet, everything is digital. So analog communication was needed to provide a base that how do physical systems work. But over those physical systems, we put a layer of abstraction and work in a digital world.
Sir, so are digital and analog communication systems two different things, or is a
It,
digital communication system a implementation of the analog communication system
so
that we have
analog
discussed?
communication, the tricks that you learn in analog communication systems, or that the tricks that you have learned so far, AM, FM, you use those tricks to uh, practically implement digital communication systems.
Okay, sir.
Okay, like at the end of the day, all the nice digital circuits, all the nice digital logic that we work with has to be implemented using analog transistors. Right? The NAND gate is basically a transistor. Sorry, the NOT gate is a transistor. NAND is a combination of transistors.
Yes, sir.
So you get a clever implementation of a basic digital signal, a basic digital circuit using analog systems, and then you can treat that digital circuit. So you can basically, what you do is, a NAND gate is a combination of transistors, but while working with digital logic, you don't actually talk about the gain, the bandwidth, the phase out, and all that, the CMR, all that crap about an analog circuit, or you don't need to go in as much detail about a digital circuit as an analog circuit. You say, okay, Digital circuit, 0 is 0 volts, 1 is plus 5 volts. I apply a 5-volt power supply and I implement any digital logic as a block. And you can view all digital circuits as blocks. You don't need to go into the exact physics of each component. That's the power of digital communication. You can view all these analog tricks as blocks. Now that okay, I know how this block works, it will work everywhere. Do I get my point across?
Yes, sir.
Yeah. So that's why we are so obsessed with digital. And and there are error correcting codes. So digital communication systems are so important. And now, as you pointed out earlier, that you have these 3 blocks additionally in a digital communication system, and correspondingly these 3 blocks in the demodulation part. So we'll try to cover A to D conversion and source coding in this course, and channel coding will exclusively be left to the next course, because you can get away. Actually, you can get away with A to D. You can get away with this as well. Or out of these 3 blocks, if you don't have anything, then you get analog system. If you do A to D conversion, you get a basic digital communication systems, and source coding and channel coding are mere add-ons that help you improve the efficiency of communication. So I don't know how much time will we have, but what I target is some basic source coding, baseband digital, baseband digital communication. Fine. These 3 things. So A to D conversion is the first step in digital communications, and further involves 3 steps: sampling, quantization, and coding. Yes, we have 7 classes left. So let's see how far we can go.
And sir, is the reference for this same?
Simon Akin, yes.
Okay.
I won't be. So next semester we'll be following Gallagher's book. Jumping onto Gallagher's book right now would be hard for everyone. So this semester for the rest of this course we'll follow Haken, not even PoC, because PoC you have certain elements that I would rather not introduce at this stage.
Okay, sir.
Okay, so we'll follow Haken. So the first part is sampling. So I'd just give a qualitative overview of these. So basically,
Sir, we have a
yeah,
class at 4.
yeah. Okay, so we'll continue on Saturday.
Okay, sir.
Okay then.
Thank
Bye.
you, sir.
Have a nice day, all
Bye.
of you.